Hello, everybody. My name is Chris Mancuso, and in this video, we're going to talk a little bit about more in depth about kind of what is going on with the GenePlexus web server. In the video description to this, there should be a link to more of a run through of how to actually use the tutorial in practice. This one is trying to give a little bit more background information. This work was really supported by Michigan State University and NIH. Okay, so there's a few things we'll talk about is what is the problem GenePlexus is trying to address? How does it work? How does the web server actually, how is it actually implemented? And then there's just a link to how to navigate the GenePlexus web server video. So what is the problem GenePlexus tries to address? So genes, they participate in all kinds of different processes, diseases, and traits. And so what GenePlexus is trying to do something called computational gene classification. So if you take a set of genes of interest, can we computationally predict other genes associated with the list? And so what does that mean in practice? There's kind of two different flavors that this could be useful for. There's kind of a bioinformatician use case and kind of like an experimental biologist use case. So for the bioinformatics, there's many databases out there that have sets of genes, like the Gene Ontology, DisGenNet, the Mouse Gene Informatics. There's a lot of these databases that have a process trait function, and they have genes associated with it. However, many genes don't have any label to any of these things. And also the sets that are in there are probably incomplete. So the idea is, how can we computationally predict the roles of these genes? And so that's one of the use cases is that GenePlexus could be used for, is that taking these pre-known sets and kind of trying to fill them in. And for the biologist case, so any omics experiments can generate a set of genes of interest. However, sometimes these measurements might be noisy, or the platform or the sample prep protocols might systematically exclude measuring a set of genes. So what we can do, an experimental biologist could do is upload their gene list of interest and see if there's any other genes in the genome that are associated with the list. So those are kind of the problems that GenePlexus is trying to address. So how does this normally done? A lot of times this is done with sequence similarity. So you have a gene, it participates in a certain function. You sequence, you look at the sequences of other genes, and if the gene 1 is similar to gene 2, then you can say that they might be functionally related. This is a very common method used and generated lots and lots of amazing results. However, the genetic sequence in every cell is assumed to be the same, but genes can behave very differently in different contexts, in different tissues. They behave in different diseases. So just looking at sequence similarity might be a little bit lacking. So there's another branch of kind of computational gene classification, which relies on networks. So over the years, many people have been performing experiments trying to determine if genes or proteins are related to each other. And these interactions can be context specific. And in the past decade, lots of work has gone into making these genome-wide networks with high gene coverage, getting pretty dense edge overlap, or edge coverage too. And they can come in all kinds of different flavors. So some are based on just physical interactions, like a big one is called BioGrid. And there's other ways that you can aggregate data across many different databases. You can use omics data, and also physical interactions, combine all these things. And a couple of other networks that do this are something like the string networks or the giant networks. So you can make these networks, and they have all of this information in it about how genes are related, or genes and proteins can be related to each other. So how does GenePlexus try to leverage that information? So a quick tutorial about basically what is machine learning is that we use linear models for our case. And so basically what you can say is that you can have two different features. This is 2 dimensions, so you can measure a variable x1, measure a variable x2. You put in what your model will predict. You'll start with some random b1 and a beta 1 and beta 2. You'll put in your measured value, then you'll see what, if you predict the right class, and if not, or if you do, there's some error function, and then you can update the weights based on it. And then you put in data after data after data, and then you try to make these beta coefficients as best as possible. So that, you know, if you start with known data like the red and the yellow here, if you put in a blue one, then you should be able to classify that it belongs to the yellow class. So that's kind of binary classification in a nutshell. So you can do it in higher dimensions. So you, instead of having 2 dimensions, you can now do, you know, x1, x2, x3, x4. Now this is, you know, not really very easy to draw on a screen, but this is what it is. And so there's some different problems. And usually what happens is x1, x2, x3, x4, which are referred to as the features of the model. In a classification problem, you have to engineer them a lot. Like, so if you're going to say, what makes you want to classify if someone's Democrat or Republican? You know, you have to think of things that you might want to measure to see if those things, you know, because you think they might have some kind of play in this, you know, so maybe the state that you live in, your age, your ethnicity, your income. And so you have to kind of design these, but there are a lot of problems that feature engineering is just too hard to do. It's real confusing about what the feature should be. You have to design these features every single problem you want. However, a very interesting method that has been being used over the past few years, it relies on the social network of people. So if this is, say, the figure up there on the right is someone's social network. So we're gonna maybe like look at the cat social network. Then, you know, instead of kind of actually looking at the like some features of this, what you can do is you can just use the features for this person as the other person's neighbor's connection. So is that person connected to that person in the network? And so other people now become the features of the machine learning model. And so what you can do now is you can make a prediction for, you know, whether the cat is going to be a Democratic or Republican based on the the connectivity of that cat to all the other people. And the way that this works in practice is that what you can do is you can make a matrix that is kind of the people by people, where people are going to be the training examples as well, and people's connections will also be the features. And what you do is you just then set labels to a few people. So you can say there's a few people that are going to be positive for this class, some people who are going to be negative for this class, and then you can predict the class affiliation for all the unknowns. And instead of having to redesign features for every single classification, all you would do now is change which of these examples have positive and negative labels. So Democrat and Republican, you'd have a certain different labels for each of these that you know and don't know. And then if you wanted to predict if someone liked the movie Cinderella, you would then just change the labels, and the positives would be people you knew who loved Cinderella, negatives would be people who you knew who did not like it. And then you can train it to see if someone you just didn't know, whether or not they would like it or not. So that's how people do kind of this social classification. It's using social networks to do classification. The same things works for genes. So and what you can do is you can use these molecular networks and take the interaction of a gene to all other genes in the network. So now the examples are genes, features are genes, and then you can say labels. So now if you're going to look at biological process 1, you know some genes participate in that process, you know some genes don't, and then you can train a model. And then without doing any other feature engineering, you can just go to another biological process, say, I know some positives for this, know some negatives of this, and train a model. So it allows the use of a lot of information that's in these molecular networks, and it allows to be able to train on a number of different interesting questions. And so our method, which was published, it was done a lot. It was done work with me, Chris Mancuso, and a graduate student, Remy Liu, where we really benchmarked this. We looked at different feature representations. So what we did is we really compared it to label propagation, which has kind of been like the state-of-the-art way of doing network-based gene classification. And so you can represent the networks with the adjacency matrix, but that is just using the exact values kind of that the network gives you when you download it. You can take that information of every single edge, and then you can use a diffusion with random start with rewalk, and then you kind of like spread that information over the edges. So that's what we call the influence. Not pictured here is you can take the network and then you can embed it with we use something called node-to-vec. And so you can embed it into a lower dimensional space, because some of these networks are, so if you look across here, the number of features are going to be the number of genes. So that's usually going to be at least 20,000 features. And so then we compared it to a label, and we used a lot of different validation schemes. We used temporal holdout, we used study bias holdout, which one we used for most of them, because not all data sets or databases have exactly the timestamp of when they were studied, but study bias holdout is kind of, you train with models that have been shown up in PubMed more, and you try to predict on genes that show up in PubMed less. We use a bunch of different metrics. Some of the precision ones we're looking at about our top predictions good. That's kind of what we stick with. We also looked at AUROC and things like that. And we did a whole bunch of different classification tasks using a bunch of different databases. And we used a few different networks. So this method was benchmarked. And if you want to see more information about exactly how it was benchmarked, just see the paper that's cited below. Oops, let me go the other way. So how is the GenePlexus web server actually implemented? So what happens is the user first interacts with the web server on their browser. So a user is going to go to the website, and then they can upload a list of genes that they think go together for whatever reason. Whether they did an experiment themselves and they found these genes to be interesting in their experiment, whether it's someone else looking at, like, a disease pulled off of this gene net, and they just kind of want to look at that gene set and see if there's other genes that our model will associate with them. Then the user will then select, which network representation to use and how to select the negatives, whether it's based on diseases or function, biological processes, and we do the negative selection automatically. So the user selects these things. Then what needs to happen is a machine learning model will then be trained with using the list of genes that the user selected. So a user will get a custom trained machine learning model for their problem. However, these models are pretty big, 20,000 features, thousands of examples. So it takes a lot of memory to kind of run these things. The jobs are pretty short. It only takes a few minutes, but it's really dedicated. It's like very expensive to have a server that can have that much memory to be able to train machine learning models, especially, web servers like this, there's a lot of downtime. So what we do is when a job is hit on submit, there's a Docker container that sits somewhere with the information to run the job. And then we put that container, we containerize that container, then is launched on Microsoft Azure with the appropriate researchers, trains it for a few minutes, and then is automatically deleted as the job completes. So it's a very, very cost efficient way. A lot of work has gone into how to optimize being able to train jobs like this for users upon a click of a button and not have it be incredibly expensive. So this is actually a very, very elegant, nice solution to have someone be able to train a custom machine learning model for themselves as soon as a button is hit. So then after that, then the user is given a link to view the job results. We tell about the prediction of how associated every gene in a network is to the given input set of genes. We also try to do some interpretability. So we have pre-trained a whole bunch of models on diseases and biological processes. And so we can take the model weights of these pre-trained models and compare them to the model weights of the user trained model. And so we can kind of figure out how similar the user trained model is to other biological processes and diseases. And then we also allow the user to view the network connectivity of the top predicted genes. So that's kind of how it's implemented. Then, yep, so if you want the hands-on tutorial of kind of how to walk through the web server, there should be a link in the video description below to link to that video. Some acknowledgements. So this has been a collaboration at Michigan State University between the Department of Computational Mathematics, Science, and Engineering for the web server. Building this web server, it's been me, Chris Mancuso, and Arjun Krishnan. And then also the data science group and enterprise services. It's been Patrick Bill, Douglas Crum, and Jacob Newstead. And so Arjun and I have been kind of the researchers who developed the method, and we kind of wrote the backend data. But then Pat and Doug and Jacob have done all the cloud building, the web interface. They've also contributed a lot to like how to make the models faster, do all these kind of things. So it's been a real collaboration between all five of us. And so we hope you like the GenePlexus web server product. If you have any questions on the web server, there is a contact page. Don't hesitate to send an email. We will get back to you as soon as we can. Thank you for your time.